the correlationship between the wind speed and sea surface temperature normally. And so it's very common in the world's ocean is when you have high wind speeds, you tend to mix the ocean more, and that's when you have a colder, anomalously cold ocean. So he's looked at summers, and you see that most of the world is blue, so wind speed and SST are negatively correlated. And this is all on this time scale, which is a subseasonal time scale. But there are some regions of this map which stand out in red, where the correlation is positive. So high wind speed is correlated with high SST. And the northern Indian Ocean is one of those regions. It's hard to go into precisely all the reasons for that. One of them is the monsoons. The monsoons occur in summer. The ocean is warm. And I'm going to show you that the ocean doesn't always cool off as you might expect in other regions where you have very strong winds, particularly the Bay of Bengal. It doesn't cool off, and it continues to feed the monsoons in some way, and the subseasonal variability. Oops. So one of the themes that I'm going to try to bring out here is this relationship between ocean winds, atmosphere, but the part of it that I'm going to try to play up here is the relationship between the precipitation and hydrology having a feedback on the oceans itself, then modifying the ocean structure, modifying the SST response of the ocean. So in this talk, I'm going to try to put forward a hypothesis that came out of one of the programs, a series that I worked on, and it came about from several observations that we took in the Bay of Bengal. It's still a hypothesis because it's kind of loosely framed at this point, but I'd like to say that the input of fresh water to this part of the world's ocean, and I'm pinning my entire talk around this hypothesis, really changes the sea surface salinity. And so if you look at a map of sea surface salinity, and the tropical oceans, this part of the world's oceans, really stand out for their low salinity. And that's because of all this precipitation and runoff that comes into this part of the world's oceans. That fresh water alters the density structure. It creates a very stratified ocean. But it's not just the stratification that matters. What happens is that the salinity starts to control the density, creating what we call barrier layers in this part of the world's ocean. That alters the sea surface temperature's response, and so the SST responds differently than what you might see in another part of the world's ocean when you're cooling the surface. That alters the effects of winds. The winds don't really mix the ocean to the extent that you would expect. It alters upwelling, and hence it feeds back and alters the biogeochemistry and the phytoplankton productivity. And to some extent, we can see this by contrasting the Bay of Bengal and Arabian Sea. The Bay of Bengal is much, much fresher than the Arabian Sea, and this salinity is stirred around by the eddy field in the Bay of Bengal. This is from a model from NRL, and that fresh water is evected out, but you can see a very different behavior between the Arabian Sea and Bay of Bengal because of this fresh water there. So I'd like to point out that also as the winds reverse, of course, you all know that the circulation reverses. And what you can see here is in the winter, this fresh water is carried out of the Bay of Bengal in a boundary current that goes around Sri Lanka. And that's one of the routes through which this fresh water is exchanged, but a lot of it is also exchanged through the eddies. And in the summer, the flow is the opposite direction. Arabian Sea water tends to come into the Bay of Bengal. So the Bay of Bengal is kind of has to be flushed on a certain time scale. All this fresh water coming in has to leave. And similarly, the Arabian Sea has to be losing salt all the time. So I want to start by showing you a few sections of from a ship that were taken in 2013 on an Asiri cruise by us. And it's pointing out to you this upper ocean structure that's very unique to the Bay of Bengal that I'd like to show you. So the top plot is showing you density. And these were sections that we took from a ship, starting out from Colombo, went north, came back down. Those are the sections. And here you're looking at salinity and temperature. And the interesting thing about this, and I'm going to show you a small subregion of this later on, what happens because of the instabilities, is that this region is very highly stratified. The stratification is much, much higher than you would expect in other parts of the ocean. And I'll show you some figures of that. As a result of that, when you try to look at mixing, any measure of mixing, it seems to be very, very low. So even when the winds are really blowing, even during the winter when the surface is cooling, we found that there was hardly any mixing subsurface of 40 meters below the mixed layer. So this is a really quiescent ocean in terms of diapicnal mixing or diffusivity. But if you look at one little piece of it there, and we put this little black box, we initialized a model with that, and you allow that model to play out, then you see that there are a host of instabilities. We call these submesoscale instabilities in the surface, and these are due to fronts in the salinity field. So the density in the upper part of that ocean is controlled by salinity. Those strong fronts are going unstable. They create a very strong vorticity field, but that submesoscale vorticity field is in the upper part of the ocean, and that's tied in with a mesoscale eddy field which fills the entire ocean basin, which invokes the thermocline. So the density gradients in the thermocline above that are riding these salinity density gradients which go unstable and create a really rich field of smaller scale eddies than you might expect. So if you look at now the density ratio, and the density ratio is, the top figure there is showing you the vertical density gradient due to salinity. So this is ds dz, and this is dt dz, and it's pre-multiplied by alpha and delta s. Then you can see that the stratification in the upper part of the ocean, there in the Bay of Bengal, is governed entirely by salinity, and in the thermocline, which lies below, the stratification is governed by temperature. So there's this breakup in the stratification, salinity controlled and temperature controlled, and I'll show you how this comes into play. So one of the ways in which this comes into play is the barrier layer, and I'm showing you some profiles from the cruise. So this is a salinity profile that was taken, and this is the original salinity profile in dark blue and the original temperature profile. And this was in winter, and now if you start to cool the surface ocean, what you find is that the temperature keeps dropping, but it doesn't overturn. It doesn't overturn because there's a barrier layer and it's stably stratified in salinity and density. So you have to cool considerably before the water becomes denser, breaks through that barrier layer, mixes, and then homogenizes over that layer, which was an isothermal layer before. So if I look at this point, P1, and I plot the temperature as a function of time, the temperature drops very rapidly when you start cooling the surface. When you mix in the layer below, it warms because there's heat trapped subsurface, and then it cools again. Here's another example where the surface has been cooled for several days, and it keeps cooling, where now the surface temperature is much lower than the subsurface temperature, and so there's heat trapped subsurface. So when you cool that surface ocean in the winter, it doesn't give up its heat easily. That heat is retained, and it's given up over time, sometimes several months. And so that heat then helps to warm or helps to evaporate water later in the season. So here's another example of that, showing you here salinity, a salinity section and a temperature section here. And what we've done, the experiment that we've done is set the surface temperature of the ocean to 28 degrees Celsius, and then calculate to what depth it would mix. So if you set the surface temperature to 28 degrees Celsius, the ocean would mix up to that blue line, but subsurface of that, there would be water that's warmer than 28 degrees Celsius. So if I plot the heat content, above the isotherm, that's the 28 degree isotherm, then it's this black line. And if I plot the heat content that would be released to the atmosphere if the surface was set at 28 degrees Celsius, it's that blue line. So the ocean doesn't really give up its heat very easily in the winter, and that affects the way in which air-sea interaction is played out. So another thing that I wanted to point out is the horizontal salinity gradients. So here we are looking at horizontal gradients in salinity along the ship's track, and that's the red line. The gradients have been scaled by alpha and beta so that they are in equal density units. And the blue line is showing you sea surface temperature. So it looks like sea surface temperature is very uniform compared to salinity. All the fronts or the horizontal variability is all due to the salinity. Now, if you blow up a region like that, a smaller region of that section, and you look at it, once again, you see that the fronts are in salinity. But if you blow this up further, you start seeing that salinity and temperature are now compensated. So this is quite different than what you see in other parts of the world's ocean. There have been several papers that talk about fronts where you see salinity and temperature compensation. And those fronts then stop being fronts because some mixing has occurred, and then salinity and temperature compensated, and there's no longer a density front. What you see here in the Bay of Bengal is that the fronts are largely because of salinity. They are uncompensated, and they're uncompensated at all scales until you get to the smaller scale. That's just the opposite of what you saw people have seen in the Pacific. They're compensated at all scales. So here you start seeing a scale-selective compensation of the fronts, and I'll explain why this happens in the Bay of Bengal. This is during the winter. So here's a numerical simulation which essentially tells you why this happens. I'm showing you an idealized front of salinity, looking at the surface view at top and a cross-section across the front, surface view of temperature and a cross-section of temperature. The temperature is uniform. The front is just in salinity. And this front is now cooled with the surface. Oops, sorry, it was playing. And it's cooled at the surface. And what's happening is that the front is becoming unstable. As the surface is cooling, the SST is dropping the most in the regions where it is most stratified. So the shallow mixed layer is going to cool more than the deep mixed layer. But the region where you get the maximal cooling is right at the front because the fronts are slumping and creating extra stratification right at the slump. So at the front. So the regions that are stratifying, the highest stratification is where the SST is the lowest. And so you start seeing filaments in the SST, and this is a still picture of that, showing you a time sequence of that. That's what it looked like initially. After 14 days, you see these cold filaments in SST. And these cold filaments in SST, I like to think of them as fake filaments in the Bay of Bengal. And the reason I say that they are fake filaments is that in other parts of the world, you'll see cold filaments where you get upwelling. And I'll show you in the Arabian Sea. Where you have upwelling, you have cold water. That cold water is connected subsurface. It's bringing up nutrients. It's bringing up low oxygen water. Here in the Bay of Bengal, where you have cold filaments, they are the regions with the maximal stratification and the least communication with the subsurface. So they are fake in the sense that they don't carry nutrients and enhance the productivity at the surface. And as a result of the fact that those fronts are slumping at the submesoscale, if you look at the compensation of the fronts on different scales, so these are at the 3 different times, and you're looking at 10 kilometers in green, the compensation or the density ratio, and at 1 kilometer, you see that the compensation occurs, or the density ratio becomes about half at scales of 1 kilometer, but the compensation doesn't occur on the larger scales. Okay? And so this, in a cross-section here, you can see that the coolest regions are right at the front, and if you take a surface, like a surface section across the front, you see that the salinity has become compensated right here. So that's the salinity front, and the temperatures become compensated right at the front. So here's an image of satellite, SST, SSS, and chlorophyll, showing you both the Bay of Bengal and Arabian Sea in the winter. And what you can see here is the Arabian Sea. There's cold water there. The SSS, it's very salty, and that cold water is associated with some upwelling, and you get these huge blooms of chlorophyll. If you look at the Bay of Bengal, you see that there's also cold water there, but that cold SST is associated with shallow regions, so highly stratified regions, and slumping fronts. And so if you look at the chlorophyll, you don't see the same impact. So I'd like to talk a little bit about the role of this stratification now in the biogeochemistry. And this is showing you that we talked about it being an OMZ. But one of the reasons, and here's from Argo data, you can see that the oxygen minimum zone is increasing in the Bay of Bengal as you go northward. And we had this data, but Eric Desaro plotted this from Argo data too. And so in what way is the OMZ here different than the OMZs of some of the upwelling margins. And to look at that, what we did is we plotted density here, the oxygen saturation and fluorescence, and we have compared the Bay of Bengal with the Peruvian upwelling region. And what you can see is that the stratification in the Bay of Bengal is very, very high. The productivity, or at least in terms of the relative fluorescence, is not as high. In fact, it's very weak compared to other parts where you have strong upwelling regions bringing nutrients up. But it's this high stratification that prevents the ventilation of the oxygen minimum zone. So the reasons for the oxygen minimum zone here are quite different than they are in the upwelling regions. So I told you that we would try to look at the Arabian Sea, which was different from the Bay of Bengal. And here is a monthly map of the sea surface temperature anomaly. This is just in the Somali Current region. And what you can see is that when you go from April to May, and then the monsoon starts, so this is the time when you start getting a strong southwest monsoon, you get very strong upwelling at the coast. And this very strong upwelling brings down the SST, and you see these beautiful filaments of cold water emanating from the coast, and those are associated with big blooms in phytoplankton. So that's the chlorophyll for the same months. And even in the northern Arabian Sea, you can see that the chlorophyll is very strongly associated with a winter upwelling when the winds come off the continent. You don't see that kind of relationship in the Bay of Bengal. So here's the chlorophyll in the Arabian Sea seen in February, and you could produce these beautiful blooms. And in fact, often NASA puts out these images for the Arabian Sea, but not for the Bay of Bengal. There's a reason. Okay, so I'd like to point out to you some differences in how these oceans respond by showing you the SST in the summer. And so this is April that you're looking at, and you see the northern Indian Ocean getting very warm. And now when the monsoon starts, so the winds are from the southwest now, you can see this region of upwelling right here, this coast, the cold water because of the upwelling, and you can see that the Arabian Sea is actually influenced by the very strong winds. But the Bay of Bengal remains warm, and it remains warm, and even though it cools down in patches, that temperature bounces back up. And that's because the ocean doesn't really mix deep and it doesn't bring up this cold water even when the winds are very strong. And you can see that in a mooring record. So I'll show you the record from this mooring. In the Bay of Bengal, it's at 18 north. So this is the seasonal cycle. And this is the summertime. So the SST drops during the summer. And every time there's an active phase in the monsoon, the SST drops, but it bounces back up. It drops, it bounces back up. And so the Bay of Bengal is able to sort of sustain these oscillations because the sea surface temperature never becomes completely cool everywhere, even though the winds are blowing really strongly. And that's different than other parts of the ocean. So we are trying to now, in a second phase of the study, trying to look at what sustains these oscillations between ocean and atmosphere. But when you look at the summer, you see these drops in the SST, and it regains that. You see a very strong diurnal cycle, which also is indicative of the fact that the surface ocean is not mixing in very well with the strong winds. So the Bay of Bengal is also a region where you get a strong genesis of cyclones and storms. And that, again, I think has to do with the fact that the sea surface remains very warm. So both this oscillation and the warm sea surface being a site for the generation of storm tracks is something that we can contrast between the Arabian Sea and Bay of Bengal. Okay. So I'll end there by saying, just by summarizing, that I think that the northern Indian Ocean is very strongly influenced by the monsoons, by the runoff, by the fresh water. It creates two contrasting ocean basins, the Arabian Sea and Bay of Bengal, and the influence of the fresh water both in affecting the density and controlling the density, hence the sea surface temperature behaves differently. The response to the wind stress is different, upwelling is different, and that plays in and affects the productivity and biogeochemistry. Thank you.
All right, we have some time for questions for Amala.
Do you see big differences in sedimentation rates in the? Do you see big differences in sedimentation? I'm just going to say it.
Go ahead, yeah.
Do you see big differences in sedimentation rates between the two basins, or is it compensated, is the lack of productivity compensated for by the increased riverine runoff?
Yeah, so I haven't made it, I don't know how many sediment trap measurements there are in, and somebody else could speak to that, but in recent times, I don't think that there has been. Can anybody from India say whether there's been a difference? Have there been many studies on looking at export flux in the Bay of Bengal or Arabian Sea? I think this is something that maybe we want to put on the table for doing, and I think that would be really, really interesting.
Yes.
Yeah.
I think Jim's arm is up first.
I was just wondering if there are any long-term trends in the nutrient inputs into the Bay of Bengal that would have affect primary production, kind of analogous to the Mississippi dead zone.
Yes, so again, I'm not aware of those studies because our work was not coastal, but I'm sure there are, certainly with the use of fertilizers, an enormous input of nutrients. And so the coastal zones, I think you would probably see a huge change when we come away from the coast. So we were 200 nautical miles out away from the coast. And there, by that time, a lot of this is gone. So, you see the influence of the Ganges and satellite imagery and everything, but all that high productivity and all the particulate stuff is gone by the time, at least it's gone from the surface ocean by the time you get 200 miles from the coast.
We did made some measurements in the rivers. What we see is only the 5% of the riverine nutrients actually entering into the coast. So they are actually mostly being utilized within 10 kilometers from the coast. They won't contribute much to the offshore.
Okay, thank you.
Susan. No, you've got it. Yeah, I was wondering, a few years ago there was a lot of scientific ocean drilling in the Bay of Bengal and the Arabian Sea, and I wondered if any of those results are out yet and how they potentially help you look at the variability in the monsoon and the export fluxes, etc.
No, I know that Liviu Gyosan from Woods Hole has been doing a lot of work on the cores from there, and there's a postdoc from India working at Woods Hole right now, but I don't know the answer, sorry.
Do we have anybody else who knows anything about what's going on with the deep sea drilling? Karen or Henry?
I'm afraid that I have not kept up with the Indian Ocean. There's a big meeting coming up on the results of the Indian Ocean drilling. I know that. I don't have the detail.
So I can follow up on it. And then let's see, I think Jerry has his hand up.
Yeah, so I was going to ask you if you could project, if you started shutting down the freshwater inflow into the Bay of Bengal, would that drive the OMZ, which way would it go? Would it become more towards hypoxia, or would that ventilation then allow it to sort of dissipate? Do you have any sense for that?
So I think you would increase the ventilation if you stop the input of fresh water because you decrease the stratification.
Right, but you would also likely increase the production, so then you've got more organic matter. So that's what I'm wondering what the trade-off balance would look like if you had a sense for that.
I don't know, but right now the productivity, I think, is not the controlling factor. Both things play in, but I think that in the Bay of Bengal, the stratification really is what's controlling it to a large extent.
Right.
Any other questions? Take one more quick one, Mike.
So the Arabian Sea has an OMZ as well, and how does that compare to both the Bay of Bengal and other upwelling regions?
Yeah, so the Bay of Arabian Sea, you do see upwelling, and why is there no OMZ there? Of course, there isn't a northward extent, there isn't cold water, you don't form deep water, but at the same time, you do get upwelling. I think, I really think there's some biologist that needs to come in to address how the different organisms are at play, but I think that there are going to be differences in how Yeah, in the twilight zone, I think there's differences in how the organisms are. Nitrification or, yeah, please.
Several people in here know something about that, about these issues. As I think you know, Mike, the OMZ in the Arabian Sea is slightly lower oxygen, which has very profound biogeochemical impacts. It denitrifies. There's strong denitrification and other reactions associated with really low oxygen. And interestingly, the Bay of Bengal is also quite low, but not quite as low oxygen. And so it doesn't transition into this new biogeochemical regime of denitrification and other chemical reactions. And so that's one difference. But my understanding is that the balances between ventilation and biological oxygen demand in those two basins are completely different. And that's a really interesting question. And I think that a fair amount of progress has been made in understanding those balances in the Arabian Sea in recent years. I think that's probably less true of the Bay of Bengal. Right. Certainly in my own mind, I don't really understand those balances in the Bay of Bengal. But as Amala showed, productivity is quite weak. But then that's combined with this much stronger stratification. So that balance is completely different. It's creating even though, and they're very close in terms of, if you look at the deep oxygen profiles, it's, they're very similar. Not in terms of structure, but in terms of how low the oxygen gets.
Yes, but so the other part of this sort of contrast, Arabian Sea, the Bay of Bengal, is also these hypotheses about ballasting of material coming out of the Bay of Bengal rivers that actually really pulls the particulates out before they can actually process in the water column. So there's a lot of factors, and our understanding of why the differentiation between Arabian Sea and Bay of Bengal is still a very open question.